Welcome and thank you for joining us for our Good Titration Practice webinar for proper sensor use and maintenance. What is Good Titration Practice? Good Titration Practice is a step-by-step process in evaluating to routinely operating your titrator. Following the GTP cycle helps ensure safe, secure, and reliable titrations. The GTP cycle starts with a thorough evaluation of your current and future needs by assessing your workflows, procedures, and requirements with a METTLER TOLEDO sales specialist. With the knowledge gained from the evaluation, one can review the possibilities for titrators, sensors, automation, accessories, and software, and the features and benefits offered by each to meet the needs of the laboratory. The installation process can include a variety of offered services, once again determined from your evaluation and needs. Offered solutions such as the iPack for detailed installation steps, the EduPack designed for proper operator training and documentation, and even the MuPack to quantify your titration method uncertainty and to see which steps influence the uncertainty the most. The qualification step is determined by your quality standards. The EQ logbook and accompanying on-site service is ideal to help pass any audit with ease. One can even qualify your LabX professional titration software with the validation manuals to meet full FDA 21 CFR Part 11 compliance. Routine operation and maintenance is key to the life of the titrator. In addition to on-site service by a qualified and trained service technician, routine procedures should be set in place for periodic maintenance and quality checks. The next session explains how to properly use your titration sensor. One of the most important and often neglected aspects of properly using an electrode is the reference solution. The reference solution must always be higher than the sample solution. This ensures gravity will force the electrolyte to flow into the sample solution. This helps ensure accurate measurements and does not allow the sample solution to contaminate the reference electrolyte. The fill port of the electrode must also be open during use, or a low pressure environment may be created, and the reference electrolyte cannot flow into the sample solution. After a titration or measurement, it is also necessary to remove the sample from the sensor before placing it back in the storage solution to avoid contamination. As seen in the previous video, removing the storage solution from the sensor, a squeeze bottle and rinse beaker can also be used to remove the sample solution before the sensor is placed into storage. Another option for rinsing is to use a dip rinse effect with a reserve titration beaker. When using an automated sample changer, the power shower can be used for effective rinsing of all titration components, including the sensor. If more thorough rinsing than just one rinse coming out of the sample on a sample changer is necessary, a dedicated rinse beaker can be used. Rinsing of viscous, organic, or dirty samples may require 2 rinse steps. Polyol titrations typically require 2 rinses. The first rinse, such as acetone or MEK, removes the polyol and solvent from the sensor. The second rinse, such as isopropyl alcohol, removes the first rinse and prepares the sensor for storage. The next session explains how to properly use your titration sensor. All electrodes come with a sensing tip and reference junction stored in the same reference electrolyte in the electrode. This ensures no contamination during long-term storage. All electrodes have the reference electrolyte in the electrode and recommend long-term storage solution stated on the head of the electrode. Please note, some sensors are stored dry for long periods. Always consult your operating manual for storage instructions. For short-term storage, in between samples, overnight, or for just a few days of no use, a couple of rules should be followed. Do not allow electrodes to dry out in the air. Avoid letting electrodes sit in a titrated sample in order to avoid contamination of the reference electrolyte. Do not store electrodes in deionized water. The DI water can remove the electrolytes in the reference electrolyte. Metal ring electrodes should be stored short-term in their reference electrolyte. pH electrodes should be stored short-term in a solution to reactivate the pH-sensitive bulb. pH 4 buffer is ideal for this, as it has a dilute concentration of hydrogen ions and many ions in order to avoid it removing electrolytes from the reference solution. A very dilute acidic solution in water, or in addition to the reference solution, can also be used. Even a pH 7 buffer can be used for a storage solution and may be preferred over a dilute acidic solution when testing for very low levels of acid or base to help avoid sample contamination. The park function of a titrator and sample changer allows for automated storage in a designated solution after a series of samples are finished being analyzed. The following section describes proper sensor cleaning and maintenance. Over time, even if the procedures are followed regarding the reference electrolyte level and fill port opening, the reference electrolyte will become contaminated. It is suggested to remove the reference electrolyte and exchange it once per month with normal use to avoid overall contamination and increase concentration of the reference electrolyte from slow evaporation of the solvent. When emptying and refilling the reference electrolyte, one may introduce air bubbles into the tip bulb. Air bubbles can be removed by holding the electrode upright and lightly tapping the side until all the air bubbles rise to the head of the electrode. An alternate technique is to firmly grasp the electrode at the head and whip or move it in an arc to push solution to the tip of the electrode with centripetal force. This will displace the bubbles and allow them to rise to the head. Ensure you have a very firm grasp when doing this to avoid throwing your electrode across the lab. The glass tip of a pH electrode is doped with metal ions that allow the conductance of hydrogen ions, as well as a gel layer of hydrogen ions on the bulb. These hydrogen ions can become depleted with use, especially in caustic or non-aqueous solutions, and need to be replenished. Similar to the slow recharge of storing a pH electrode in a pH 4 buffer, a stronger solution can be used for more powerful recharging. Stirring or storing the electrode in a solution of approximately 0.1 molar acid can thoroughly recharge the bulb. It is very important to thoroughly rinse the electrode with DI water after recharging and perform another calibration if calibration is needed for proper use. The tip of a metal ring electrode or sensor can become coated with analyte over time. In addition to emptying and refilling the reference electrolyte once a month, the metal should be polished to remove contaminants. The suggested monthly frequency may need to be performed more often in QC environments with heavy use. A number of techniques and solutions can be used to polish the tip metal, including wetted aluminum oxide powder or high fluoride toothpaste on a towel. One can also use a fine emery cloth designed for polishing silverware or jewelry metal. Pictured here is the silver ring of a heavily used DMI 141 electrode, before and after polishing with toothpaste and a heavy paper towel. One can see the black tarnish removed from the silver on the towel used for the cleaning. A ceramic reference junction can be contaminated over time with sulfides, proteins, or silver chloride precipitate. This contamination can block the flow of the reference electrolyte and must be removed. Pictured here is a silver ring electrode with a ceramic reference junction contaminated with sulfide. Sulfide contamination can be removed by stirring or soaking for 1 hour in a solution of 8% thiourea and 1 molar hydrochloric acid. Protein contamination can be removed by stirring or soaking the electrode for 1 hour in a 5% pepsin and 0.1 molar hydrochloric acid solution. Silver chloride contamination can be removed with an overnight, approximately 8 hours or more, soaking in 10% ammonia. This must be followed with a thorough rinse and soak in a dilute acid. The following section covers calibration of a sensor, as well as evaluation of a sensor through calibration data and other tests. Not all titration sensors require calibration. If performing direct concentration measurements, such as pH, or a titration having an endpoint established based off a concentration value, such as a titration to pH 8.3, the used sensor requires calibration. an equivalence point titration, which utilizes an inflection point determination based off the first or second derivative of the generated titration curve, does not require a sensor calibration. Calibration yielded data, such as slope and zero point, are indicative of the performance of the sensor's ability to provide accurate measurements. So, even if a calibration is not required, calibration methods should be in place for troubleshooting and performing quality checks of your sensor. A kinetic test can also be used to test the ability of your sensor to respond to potential or concentration changes fast enough for it to be suitable for your titration method. A good practice for sensor calibration is to make sure you calibrate at least daily and preferably twice per shift if using the calibration data for measurements or endpoint titrations. One should always bracket your measured points with calibration standards. For example, calibrate with pH buffers 7 and 10 when measuring samples near pH 8. Use buffers at least 1 pH unit apart and preferably no more than 3 pH units apart. Always use fresh buffers in order to avoid air contamination, especially with buffers that are greater than pH 7. Buffers should not be reused when accurate measurements are desired. Calibrate your sensors at the same stir speed in which you measure or titrate. Also calibrate at the same temperature as you measure or titrate. These last two steps help ensure consistent ion activity from standard to sample. Pictured is an ideal linear calibration of a pH electrode using pH buffers 4, 7, and 10. In reality, performing a linear calibration with more than 2 points, calibration points rarely perfectly align. The line of least squares, also called the best fitting line, is then plotted as the calibration line. The segmented calibration in METTLER TOLEDO pH meters and titrators is preferred to avoid the possible errors that could arise from a linear calibration. A segmented calibration yields separate calibration lines from each calibration point to the next. This yields multiple 2-point calibrations and negates any errors caused if the line of least squares doesn't perfectly align with all the calibration points. In extremely high or low pH solutions, electrodes can experience an alkali or acid error. This is caused by either too many hydrogen ions present in solution or too little hydrogen ions in and on the glass pH bulb. Near these pH values, segmented calibrations are most useful as the calibration line deviates from a theoretical straight line. Data from the calibration is used to calculate concentration from potential when measuring or titrating samples. This is seen in the example graph and line equation for a pH electrode. Ideal slopes for a sensor depend on the ion being measured. Most ideal slopes are displayed in the table. The ideal zero point for a pH sensor is pH 7, and for sensors measuring in parts per million or PM values, it is 0 parts per million or 0 PM. Many meters reference the slope in terms of percentage. This is simply the percent to the ideal slope. Consult your operating manual for suggested slope and 0-point limits. Typical slope limits are 90 to 110% or the millivolt value equivalent. The kinetic electrode test measures the speed at which an electrode can adapt to changing potentials. ASTM D664 for TAN of oils also references this test as a quality check of the electrode. Step 1 is to ensure an electrode has a stable signal in a solution by measurement or just allowing it to stand in a solution for a couple of minutes. Next, the electrode is moved to a solution that yields a different potential, such as one pH buffer to the next, or different redox potential solutions for a redox electrode. Immediately start tracking time from the solution change. After both 30 and 60 seconds in the solution, record the raw millivolt values. You can gauge the electrode's response speed from the difference in these two values. This value is referred to as the drift. The DP5 phototrode will need the millivolt signal adjusted over time. Weekly is suggested. This ensures that established method parameters when the DP5 was new are still valid. If using the units of absorption or percent transmittance, this establishes the baseline. Please note and make sure that the DP5 has been powered for at least 15 minutes before adjustment. Thank you for your time, and we hope to have you attend future Good Titration Practice webinars.